Test. Test. Yep, works. Where do I turn it off?
Here's the ISO switch.
This one.
Okay, good morning from my side. My name is Marc Stöttinger. I welcome you to the third day of CHES, to session 8. I hope you had a great evening after the banquet. My pleasure is now to introduce or to share you to the session of Emerging Attacks 2. The first talk we will hear is from is about illusion and Dazzle. What does it mean? It means the paper goes about an adversarial optical channel exploits against Lidar systems for automotive applications. Hocheol Shin will give us the presentation. Welcome the speaker, please.
So thank you for the introduction. As the chair introduced, my work is on LiDAR hacking. And this is a joint work of me and my colleagues, Dohyun, Yujin, and my advisor, Yongdae. Transition from human control to autonomous driving is a general trend. It's rather difficult to find companies nowadays that is not involved with autonomous driving. All these companies and many others are currently developing autonomous driving platforms or their components. Although it will not be realized in near future, humans' role in driving will keep decreasing, whereas that of cars will keep increasing. So then does how autonomous driving differ from past human driving? In past human driving, human driver took care of every important role for driving. Ears and eyes for perceiving, pedals, gear stick, and a steering wheel for controlling. When it comes to autonomous driving, humans' roles are completely replaced by ECUs, telemetries, and various types of sensors. And these together take the form of a sensing and actuation system, where a feedback loop is established. And we call it a sensor attack, that an external attacker intentionally injects malicious input to the sensors, and without adequate security features in the system, this malicious input propagates to the actuators, and because the actuators are directly connected to real world, this can lead to devastating outcomes. So this is the motivation of our work, and in our work we especially focused on Lidars. That is one of the sensors mounted on cars. So as an overview for this work, we explored the possibility of optical channel sensor attacks against Lidars. And as an outcome, we introduced how LiDAR spoofing works in detail, the process of inducing cluster fake dots to LiDARs, and the saturation attack. And we found an adverse effect of curved reception glasses mounted on LiDARs. Both attacks are demonstrated by experiments on COTS LiDAR system. We also discussed problems of current LiDAR design and possible countermeasures and their limitations. So before getting into the main subject, let me introduce some background on this topic. First, the LiDAR is an acronym of light detection and ranging, and they have lots of strengths. They are sources of highest spatial resolution, and the resolution is generally much better than that of radars and ultrasonic sensors. And this is because of the superior directivity of laser beam they use. Indeed, highly autonomous driving platforms tend to have LiDARs. LiDAR's working principle is basically the same as that of radars, sonars, and ultrasonic sensors, except the media they use. In this work, we defined the multi-layer scanning LiDAR as a rotating LiDAR with 3D mapping capability. So let me briefly illustrate how a multi-layer scanning LiDAR works. So first, the LiDAR fires a pulse to the object, and when the fired pulse hits the object, a fraction of it reflects back as an echo, with the round-trip time of delta t. And from this round-trip time, the LiDAR can deduce the distance to the object as c delta t over 2. And because the LiDAR knows the direction to which the pulse fired, a point can be mapped to a virtual space. And pulses are also fired up and down to map vertically. And for horizontal scanning, the LiDAR rotates while firing pulses. And these acquired points together form a point cloud. So there are a set of important parameters that defines the operation of a scanning lidar. First one is pulse repetition time, in short PRT. This is the time difference between adjacent pulse firings. And generally, PRT remains constant during the rotation. Second parameters are receiving time and dead time. When an echo is received by the lidar cannot determine from which it originates because it can be any of the previously fired pulses, and thus it cannot determine the elapsed time delta t. So to limit the ambiguity, each PRT is divided into receiving time and dead time, and all echoes received during the receiving time are considered as that of just transmitted pulse, and all echoes received during the dead time are ignored. Typically, the length of the receiving time is much shorter than that of the dead time. For the case of VLP16, we have tested the length of the receiving time was only 1%, only about 1% of the dead time. We can also deduce the LiDAR range, which is the maximum detectable distance, Lmax, from the receiving time, delta T max, as C delta T max over 2. The last important parameter is the receiving angle. It's the angle of receiver aperture. So when an echo or external light falls into the receiving angle, it can be detected by the receiver in the LiDAR. However, when it falls outside the receiving angle, it cannot be detected. The size of receiving angle is not to be large. If precisely calibrated, it's enough to cover echoes from the farthest point. Next is sensor attacks. In this work, we deal with two types of sensor attacks. First one, sensor saturating exploits the transition curve of a sensor. So this is a typical input-output relation, transition curve of a sensor. So in this curve, in the linear region, input changes are well applied to the output. So this is the region where a sensor is intended to operate in. However, this linearity cannot last forever because beyond a certain input level, the output signal starts being saturated. So the saturation region starts. Saturation attack is to intentionally push the input signal level to fall into the saturation region. And by doing so, the attacker can suppress the output change so that the sensor cannot notice it. Second is sensor spoofing. It is to deceive the victim sensor. It exploits a semantic gap between the real world and the sensor's perception. Taking an example of face unlock hacking, the smartphone on the left is actually seeing a display. However, it thinks it is seeing a real human face. So there's apparently a gap between two. When it comes to LiDAR spoofing, it is to make a LiDAR see an object that does not exist in fact. So let's get into the main subject. We assume the target system as a scanning LiDAR system that is exposed to the exterior. And to verify the attacks working on real LiDARs, we chose our test target as Velodyne's VLP16. It is a 16-layer scanning LiDAR system that outputs sensing data via Ethernet in UDP packets. And the acquired sensing data can be easily visualized by the official software VeloView. We'd like to note that we could not perform any destructive analysis of it because the LiDAR was not ours, but the property of our research sponsor. So for the attack model, we assume two different models for each attack. First, for saturating, the attacker is assumed to be able to inject attacking light to the victim LiDAR, and this includes aiming and focusing capability. And the attacking light has the same wavelength as the target and is strong enough to saturate it. For spoofing, in addition to the injection capability, the attacker can also receive pinging pulses from the target LiDAR. And for the induction of closer objects only, we assume the victim LiDAR has either consistent or predictable ping waveform and PRT. We'd like to stress that virtually all CHES automotive LiDAR meet this condition. Let me introduce the methodologies for the attacks. First, for saturation attack, it is conducted by illuminating the target LiDAR with intense light source. Its working principle is just as previously explained. When the receiver in the LiDAR becomes saturated, it becomes unable to sense incoming echoes, then blinded. This attack is strong because saturation effect itself is unavoidable. Although its detection is easy as long as we know we found no cost lidar with this function. Its effect takes two different forms according to the injected light strength. For relatively weak light source injection, it leads to numerous fake dots in the sensing result. And although we do not know how exactly it works, there seems to be a detection threshold. And when the received signal crosses the threshold, dots are determined. So when the lidar is exposed to weak light source injection, it makes overall noise level increase, which leads to numerous detection level crossings and generates numerous fake dots. So this is the video of how actually it looks in the sensing result. In this video, you can see numerous fake dots induced in the direction of the light source. So for strong light source injection, because the receiver is now fully saturated, there is no crossing of the detection level, detection threshold, and thus the lidar becomes completely blinded toward that direction. So this is how actually it looks like in the sensing result. In this video, the plate in the sensing result disappears when the lidar is exposed to a strong light source injection. And there are overall signal level degradation around the affected region. We also experimented an adverse effect of curved reception glass. By obliquely illuminating VLP16 with strong light source injection, we could observe fake dots not in the direction of the attacking light source. We infer the cause to be either refraction or reflection onto the glasses. And we found other lidars also have curved reception glasses, so they may have similar kinds of problems. The significance of inducing fake dots in directions other than that of the light source is that it can much widen the attack surface. For example, this attacker vehicle in the next lane to the victim can induce fake dots in front of it. This is quite critical because in the next lane, the attacker can approach the victim much closer without alerting it. So this is the video of how it actually looks in the sensing result. In this video, we illuminated the lidar from the bottom. However, dots are generated in top right section. So for the methodology of spoofing by relaying attack, I'd like to first introduce the ideal attack process to understand what's going on briefly. And for the induction of a further fake dot with this model, its process is basically the same as the previous work by Petit et al. And it's just mimicking the process of making echoes. So let's assume the attacker wants to spoof a fake dot at the distance of L from the lidar. If there's a real object at that position, after the lidar fires pinging pulse, it will receive its echo after the delay of delta t. So to mimic this process with the spoofer located at LS, after the receiver receives pinging pulse from the target lidar, the spoofer adds the delay of 2L minus LS to compensate this distance difference, and then fires back attacking pulse to the victim lidar. By doing so, the spoofer can make the fake dot look as if it were L away. The limitation of inducing further fake dot is that the importance of spoofed fake dots are quite limited because their distance is less than the spoofer itself. Then why can we induce closer fake dots with this model? The reason is simple, because we should induce negative delay to make closer objects. However, this becomes possible when we understand what's going on actually. So there are two main differences from the ideal case. First one is the laser beam diverges, so the receiver with sufficiently large aperture can detect multiple pinging pulses. And due to receiver transmitter displacement, there comes an additional delay of S until the lidar actually points to the direction of the transmitter. Based on these delays, the ideally required delay, di, is added up with little processing delay, dp. And finally, the attacking pulse is fired. So why does this make cluster factors possible? The reason is the actually required delay, dA, is sum of various delays, and because T and S tends to much larger than the ideally required delay, DI, even if DI becomes negative, DA can still remain positive. So the induction of negative delay is actually not required to generate cluster object. To verify this working on real LiDAR system, we implemented our spoofer as the diagram below. And to spoof the LiDAR, we first aimed the victim LiDAR with the spoofer, and after the photodiode receives pinging pulses from it, it converts them into electric signal and passes this electric signal to the receiver circuit. The receiver circuit converts them into a series of 5-volt pulses so that the function generator can be triggered upon them. And the function generator adds some delay and emit pulses to the pulse laser diode driver. Finally, the pulse laser diode driver let the pulse laser diode fire attacking pulses. For the induction of cluster object, we first induced the father dots and reduced the delay until we could observe cluster dots. So this is how actually looks like in the sensing result. We first induced the father dots, and in this video, we altered the delay parameter of the function generator so that the induced fake dots move forward and backward. In the next video, we set the spoofer to spoof cluster dots, and as you can see, dots are generated between the LiDAR and the spoofer. Although not mentioned in the paper, we also experimented outdoor spoofing. Although it's a little tricky to spoof outside due to sunlight, we could observe fake dots. We omitted many things due to time limitation, so please, for the details, please refer to the appendices webpage. The URL is also written on the last page of the paper. Before I conclude the presentation, let me discuss a couple of points on the attacks. First one is stealthiness. Because proposed attacks use IR, they are invisible to human drivers and pedestrians. Second, as previously explained, the minimum required receiving angle to meet the specification is not that large. For the case of VLP-16, the minimum required angle was just 0.0048 degree. However, when we actually measured it, this was much, much larger than the minimum required value. It was at least 2 degrees. So this led to much wider region affected by the attack. I'd also like to discuss possible countermeasures for saturation. Because its detection is very easy, automakers may adopt multiple sensors and program the vehicle to abandon compromised sensor output and recover them with other sensors. LiDAR manufacturers can minimize the receiving angle to reduce the size of the affected region. However, I'd like to stress that none of these is an ultimate solution because saturation effect itself is unavoidable. For spoofing defense, minimization of receiving angle also works, and by adding slight random perturbation to PRTs, we can prevent the induction of cluster fake dots. We proposed it as a detour because random probing is hard to be adopted for current rotating LiDARs due to their rapidly rotating parts. However, even with these countermeasures, the induction of a single father fake dot per spoofer is still possible. So in conclusion, we presented and experimentally verified 2 types of attacks against the CHES LiDAR system. And the results show current LiDARs are defenseless against presented attacks. Although we found some defensive measures that can be applied, it seems not enough to fully trust LiDARs. Because there are other sensors with similar working principles, they may have similar vulnerabilities against sensor attack. And finally, despite all these problems and vulnerabilities, we do not think we should completely abandon autonomous driving. But I think things have to be more robust to be realized. So that's the end of my presentation. Thank you.
Thank you for this nice talk. Are there questions? So I have 1 or 2 questions which come to my mind. First, you said one probable countermeasure would be to reduce the receiving angle.
Yes.
So when you reduce the receiving angle, the dead time will increase. So does it may impact or have some impact regarding safety? Because you have a shorter visual point. So the dead time gets bigger, the radar needs to spin faster.
Yes.
Does it impact the detection of the complete environment?
Yes. First, I'd like to point that actually the receiving angle and the receiving time has nothing in relation, because current receiving angle is actually much larger than to meet the current receiving time. For the case of VIII, the receiving time was, because the LiDAR range is 100 meters, we can reversely calculate it as about less than 1 microsecond in nanosecond scale. However, the receiving angle for current LiDAR is 2 degrees. It's much bigger than that nanosecond scale. So I think there will be no problem to for the receiving angle. Yeah.
Okay, thank you. The next question I have is, in your paper you said there's an opportunity to change the ping waveform in order to avoid spoofing.
Yes.
Would it be possible to or how frequently you can change the ping waveform? Meaning, is it possible to change the ping waveform for different angles?
I'm not sure, because I'm not a LiDAR manufacturer, but I think that would not be easy for LiDARs, because they use lights. For the case of radars, it's possible, but I'm not sure that it can be applied to. It can be easily applied to LiDARs. I think it's better to randomize the PRT. Mm-hmm. So by doing so, we can defend most of the attacks I proposed. I think that way is much better to apply. Yeah.
Okay. Thank you. There's a question.
Thank you very much for the great talk. You explained about spoofing on the angle of direction. And do you have any comments on the spoofing on the angle of elevation? I mean, this direction.
So LiDARs have different working procedures. For the case of VIII, there are identical 16 LiDArs, 16 2D LiDArs in vertically placed. So to spoof vertically, we can duplicate the spoofer, or spoofer with one receiver and multiple transmitters, so that we can, by doing so, we can spoof vertically. Yeah.
Thank you very much.
Yeah.
So, thank you again for a great talk, and thanks, speak again. So the next talk is given by Luka, Malaysia. It's about hacking in the blind. We move from automotive now more to the direction of malicious device interfaces. In the paper, Hacking in the Blind, Almost Invisible Runtime User Interface Attacks, Luka will present us his findings on how malicious interface can secretly interact with the target device in a way that the user might not be aware of it.
Mm-hmm. I apologize. Testing, yes. So, hello everyone. It is a pleasure to welcome you all here today at my presentation. This work was a collaboration with my co-authors, namely Kari, Thomas, David, and Srdjan, and all of us being from ETH Zurich. Now, every user interface, or UI for short, on an abstract level consists of two main components, namely user input and system output. Now, the most prevalent type of UIs today are still those tailored for the combination of some form of a pointing device, so think mouse, and a visual display, so think monitor. Other than performing simple daily tasks, such as maybe checking weather or news, through such UIs, users also perform operations that are critical to privacy, security, and safety, such as making e-banking payments or controlling sensitive equipment. For example, medical doctors use such UIs to configure the implanted medical devices of a patient. Now, these facts make UIs a critical component in the overall security of any system designed to be controlled by users. And attacking such UIs is the focus of this work. Now, modern malware can reside in various places, and it can reside on the device, but can also be located outside of the device as well. So, for example, an attacker could connect a custom-made malicious peripheral, and such attack devices can be readily and cheaply bought. The attacker can also compromise the link connecting the peripheral to the device, and one such example is an NSA device that's located inside a malicious USB connector. Such attacks are often known as command injection attacks. Now, the key observation that makes such attacks alluring for attackers is that they're almost always possible. And as an example of a physical attack, they're often both brief and non-invasive. But more importantly, irrespective of how well secured a computer system itself is, the attacker can almost always attack it through its UI. Such attacks, therefore, sidestep existing security measures. Now, when we look at such attacks, we can see that they are both very simple, while at the same time being reliable and highly effective. Such attacks are therefore a real problem, and it's important to research them in more detail. A typical command injection attack works as follows. The attacker waits until the user leaves, the machine unattended, then approaches. The attacker would then connect a malicious, commonly USB device that registers itself as a new set of peripherals. The device then immediately injects a series of pre-programmed input, for example, moving the mouse or typing keys. After that, the attacker would disconnect the device, at which point the machine is compromised with some kind of malware. Such attacks are also known as bad USB style attacks, and they are surprisingly effective, but they are also limiting. They rely on registering new peripherals, as well as installing malware on the system itself. Both of these steps expose the attack to detection, for example, through some sort of a host-based security approach. So think malware detection or antivirus. But most importantly, for such attacks to work, the user must not be looking at the screen. Otherwise, the attack could be detected. To better understand the limitations of such existing attacks, consider the previous example. However, this time I will change the context and move from desktop machines into the domain of dedicated terminals, such as medical devices, for example. Such devices are in many ways similar to their desktop counterparts. For example, they're also often controlled with a keyboard/mouse combination. However, they are commonly security-hardened devices that are dedicated to one particular task. Therefore, installing any application on such devices, malware included, is typically not possible, as such devices run stripped-down operating systems and commonly run only a single application. And the concept of a desktop does often not exist. Therefore, the attack we saw before would not work. But most importantly, or more importantly, serious UI attacks on such devices can only be launched while the user is present. So consider the following example. The medical device is a pacemaker programmer, and the goal of the attacker is to program a patient's pacemaker with some erroneous values. Now, the attacker can do this only while the doctor is operating the device and while the patient is present. Therefore, as existing attacks would not work, a different approach was needed. Which brings me to our attack. Now, the first part of our attack is similar as before. The attacker comes and installs the attack device. However, this time, it is installed in between the peripheral and the pacemaker programmer. It then lays dormant and passively observes all user input, and then when the device detects that the user is performing the operation that we want to attack, in this case, setting the imaginary variable of heart rate to 100, it is going to block the user input and inject a pinpoint accurate set of events that are going to modify critical fields of the user interface, for example, to change the variable to 1000. Now, the injected input is small and fast, therefore the user has very little chance of noticing the attack happening. Furthermore, if users don't notice the attack, they could believe that they inadvertently caused the damage themselves. Now, in contrast to existing attacks, R does not install any malware, nor does it install any new peripherals on the system itself, as we simply relay data from existing ones. But most importantly, we launch the attack in plain sight while the user is looking at the device and actively using it. I will now present a more detailed overview of our attack. First, I would like to emphasize the unique feature which differentiates this attack from existing ones, and namely that our attack is unidirectional. Now, this means that although our attack device has full visibility and control of the user input channel, it cannot directly observe the state of the system, as the device has no sort of system feedback whatsoever. Our attack therefore operates in a, we can say, blind manner. The device then records user events, and together with a model of the UI that we want to attack, is provided to the first major component in the attack, namely the state and location estimator. Now, the goal of this component is to, at any given point in time, estimate first where the user's mouse cursor is on the screen, and secondly, at which state the target device is, or in other words, which part of the UI is the user currently interacting with. Now, the state and mouse location estimate is then used by the attack launch component, which decides if it is the correct time to launch the attack. If so, the component would then generate and subsequently inject the mouse and keyboard movements needed to make the malicious modifications. Now, to put my talk so far into perspective, I will show you a video demonstrating the attack. Oops, sorry. There seems to be a problem. The video won't play. So in any case, I will continue and then maybe later on come to the... So sadly, as we should have seen in the video, the device was able to infer the correct time when to launch such an attack. This means that the device knew precisely what the user was doing, and this is the component that I would like to describe now. Now, when the device is first installed, it does not know where on the screen the mouse cursor is. We represent this uncertainty area, or the area where the mouse could be, in red. And initially, the mouse could be anywhere on the screen. Now, let's consider an example where the attack device observes a mouse movement upwards and to the left, by, for example, 10 pixels. Now, what you see here is that this movement would tell us that irrespective of where the cursor was on the screen before the movement, after it cannot be in the lower and right border regions of the screen, because we moved it. Therefore, we have reduced the possible locations where the cursor could be. Similarly, another movement upwards and left further reduces this area. However, not all mouse movement reduces the uncertainty, as this movement to the center of the screen, for example, will illustrate. This was how mouse tracking works, and I would like to now explain how the device estimates at which UI state the user is currently at. So consider the example application where one of the UIs is a simple login screen. The user filled the two text fields and then moved the mouse. Now, at this point in time, our device observes a mouse click. So let's see what happens. Now, since the uncertainty area is quite large, the mouse could have been anywhere inside of this red region. For example, the user could have clicked somewhere maybe outside of the two buttons. And in that case, the state would remain unchanged because no button was clicked. But we can see that the uncertainty region shrinks, and we are a bit more certain where the mouse was, since we know the user could not have clicked anywhere on the two buttons. Another possibility is that the user clicked on the login button. In that case, the UI would transition to a new state, and we would observe that the uncertainty region shrinks significantly as we are more certain or as we are certain that the user clicked somewhere inside of the area of the login button. Therefore, the mouse must have been somewhere inside. Similarly, the user could have clicked on cancel as well. Now, I presented 3 possibilities. We observed the mouse click. Therefore, one of these things did happen. But we cannot say for certain which one it was, since our attack never receives any sort of feedback from the system. We must therefore track all possibilities, all events, simultaneously. And over time, some unlikely combinations of state transitions will be removed, while the more likely ones will be tracked further. Now, consider the previous example where the user could have clicked one of the buttons or outside of them. We could argue that some of these events are more likely to happen than others. There are various strategies that we can use for this, and the simplest one would be to treat each outcome equally likely. However, we could also say that the cancel button was clicked more likely because more of its area falls inside of this red uncertainty area, so where we know the mouse is but can't say for sure where. We evaluated some of these strategies, but for further details I refer you to the paper. So to summarize, the goal of mouse and state location tracking is to continuously observe a stream of user input and to keep refining the prediction until we are fairly certain that we are in the state that we want to attack. In that case, we stop tracking, launch attack. And the attack then maliciously modifies these UI elements in a very fast way, and the user cannot see. Now, so far I have talked about tracking, and however, another important component of our attack is called UI modeling. Namely, for our device to know where in this UI space the user is currently at, well, the device itself needs to know what are all the possible UIs that the user can be at. Now, we can approach the problem of creating such UI models in 2 separate ways. First, given an application or a system, we could try to extract, we call it the complete UI model. Namely, all the UI states an application can be in. However, it's easy to see that this method is only well suited for applications that are not complex, or not too complex, and that have very simple UIs with comparably few UI states, such as medical devices. However, modern desktop applications are far, far too complex for this method, so we would never be able to map the whole UI space of, let's say, a modern browser. To make our attack work in those cases, instead of modeling the whole UI space, we can also construct a partial model that contains only the UI that we want to attack instead of all of it. And this is a method that we call partial modeling. Now, as creating such UI models is an integral part of the attack itself, we can also use it to illustrate in which scenarios can we use this attack for. And the first question we can ask is the UI that we want to attack unique? Now, what do I mean by unique? Or in other words, is there a similar UI to the one that we want to attack anywhere on the user's device or anywhere on the websites that the user frequently visits? Now, if the answer to that is yes, then we can construct a partial model and launch the attack. However, if the UI is too simple, or rather if chances are that it's not unique, then we can ask the question, is the application itself simple enough? Because if it is, we can then extract the full model and launch the attack. So either one of these two would work. Otherwise, the attack is, of course, not applicable. Now, to see how well the attack works, and more importantly, how many users would notice this attack, we tested it on 2 different kinds of security-critical UIs. First, we performed an online user study using the UI that would have been shown in the video, but maybe at the end of the talk I can show it, where the participants were tasked to program a fictitious pacemaker. Now, this UI that you see here, this is a custom UI, we created it, but we tried to make it in a way that it mimics the UIs of the real pacemaker programmers that we analyzed beforehand. Now, this was a full model attack, and after observing only 10 user clicks with the corresponding mouse and event event movements in between, we can infer with over 90% accuracy precisely where the user is in that application. So it takes only 10 clicks. This result means that our device is able to precisely infer where the user is with very, very little movement. The attack was also highly successful, as more than 90% of the users did not notice anything amiss. We also wanted to be a bit more realistic than this, so we decided to test our attack on the UIs of 3 major e-banking sites in Switzerland. Now, these were copies of the real sites. We just had them offline in a testing environment. So this was a partial UI model attack, and we tested it on users that were already customers of those banks. Now, the reason for that is that the users already knew the user interface, and they use it often. And we wanted to see, does the attack work on that kind of, we can call them experts. And our results were similar as before. Over 90% failed to notice the attack. Now, in both of the user studies, our attack operated in real time. There was no sort of lag or delay that could hint to the user that anything wrong was happening. And the majority of users, of course, didn't notice anything suspicious, even though the attack was occurring right before their eyes or in plain sight, while they were attentive and interacting with the UI. Now, how do we prevent this attack? A possible countermeasure could be, for example, through the use of trusted peripherals, such as mice and keyboards that, for example, share some sort of a key with the target system. Now, this method is also known as trusted path, and it basically means that you cannot hook in between this connection between your peripheral and the device itself, because all the data that goes through it is, of course, encrypted and signed. Now, the problem with this approach is that it requires custom hardware, and therefore more expensive. Another possible approach is that the system would somehow learn the way, or learn the input features of a user. So for example, the way I move my mouse or the speed at which I type my keys. Because, as the video would have shown, the attack works in a way that it tries to inject these malicious input events in the fastest manner possible. Now, if the system sees that I'm trying to move my mouse, at light speed, it could say, aha, wait, something is wrong. A more extreme measure would be to randomize the layout of critical user interfaces on every run. Now, this would mean that it would prevent the attack because our device wouldn't know where these elements are on the screen, right? However, this approach comes with a very high cost. I can tell you that I certainly would not want my doctor to operate a pacemaker programmer that randomly changes the position of its program pacemaker button every time you run it. So, in summary, we reviewed various possible countermeasures, and we concluded that they all have limitations. However, finding better defenses that are both practical and effective remains an open problem. Now, before concluding the talk, I would like to discuss on a few points. As of now, we have not seen any examples of this attack happening in the wild. However, we know that hardware that's capable of launching such attacks does exist. And, for example, this NSA device, for example, it has the capabilities of doing this. And as we should have seen in the video, our prototyped attack device is quite bulky and big. However, it can easily be minimized and made significantly stealthier in the process. So our attack might as well be implemented completely in this tiny little malicious USB connector right there. So to conclude, in this talk, we have presented Hacking the Blind, a novel approach to attacking systems through their user interfaces. Our attack device sits in between the legitimate peripherals. It is easy to deploy, and it is invisible to any sort of traditional malware detection because it's running outside of the machine itself, and it never attempts to install any sort of malware on the device whatsoever. But most importantly, our attack is both accurate and undetected in the vast majority of users. With this, I would like to thank you all for your attention, and I'm happy to take questions.
Thank you, Luka, for this nice talk. Questions regarding to prevent malicious input on UI?
I will try to sort the video in between.
Oh, yeah, maybe you can
But I can
prepare the
happily take
video in
questions.
between. What comes to my mind is you propose to randomize the UI as a possible designed countermeasure.
Mhm.
Do you think there are other, let's say, constructive countermeasures to make a more robust design of UIs that that your attack is struggling of identification the right point in time and position of the mouse?
So you're talking about defense mechanisms, right? So
Yes.
that would have been one of the ideas for future work, but what falls to my mind, other than this radical notion of randomizing the UI every time, another idea would be to somehow limit the amount of changes that a user could make in any given UI. So think this, you're trying to program my pacemaker and you set the heart rate value to 100. That the system itself doesn't allow you to change that value fast. That it maybe says, hey, I will allow you to change this once a minute. Or that it somehow maybe gives you feedback saying, do you really want to set this value? So these sorts of things. However, you see that one always has to pay a price in terms of usability, right? So it is an open question of how to do this in a manner that doctors especially would go with.
Okay, thank you.
Mm-hmm.
The question?
Since the system is blind, how do you make sure that your injected inputs don't cause any observable effects that the user can see?
So that was so first of all, our injected, oh, there we go. So let me just, these are the attack devices, sorry to interject. So these are the two attack devices. This is me installing the device in between. So as you can see, both of them are quite bulky at the time, but can be easily minimized further on. And regarding your question, it's going to come in a second. So then once installed, basically the device just waits until it's the precise time to launch the attack. And this is what we will see. So in this case, the goal of the user was to program the so a fictitious pacemaker with these three values down here. So the user would then go into the screen, note these three values, and then go to the program device screen right here. And then the user fills 88 in the first one, and then the two sliders. And then the user would click the program pacemaker button. Now, did any of you see what happened here in the meantime? So it was quite fast. So, sorry? It jumped, right? Yeah, okay, so you already knew what to look for. But let me say that if you think that the value that it was programmed with was 88 in the first text field, you would be wrong. Now, I will redo the attack, but just slow down, so you will be able to see precisely what happened. So then the user starts filling these values again, same as before. And then when the malware detects that you click the pacemaker programmer, it's going to intercept your click, never forward it to the system, and then it will move it up, change it, click program pacemaker, and then undo it again. Now, this whole attack is done within 100 milliseconds, so there's very little chance of noticing it. Now, to come back to your question, we try to do it as fast as we can, therefore to minimize the amount of damage that we can make. However, of course, this little thing that's sitting in between, it could have false negatives. It can say, oh, hey, now is the time to launch my attack, and it injects it, but it's completely wrong. And in that case, no harm done, because I see my mouse jumping randomly through the screen every now and then. So
I was more worried about clicking on close the application or jump to another application, those kind of things.
There's always a possibility for that to happen. But I can tell you that the attack worked on 90% of the people, and these remaining 10% noticed something. However, only one person in the whole user study noticed the attack itself. All of the other ones said something like, hey, I saw some weird movement. I thought it was a bug in the application, so I fixed it. And it tells you just how unlikely, so users just don't think that they would fall for such an attack. So they're very kind of generous in sense of the mind plays tricks and they explain what they saw in terms of what they know already. So it must be a bug.
Since you've gone this far, could you also log all the...
Sorry?
Could you also log all the key clicks and mouse clicks?
That of course you can do. But in our attack, we went much beyond a simple keylogger. Because in our attack, when you install the device, it never communicates with the attacker. So it's fully self-contained. But of course, I mean, if we stick a little RF antenna, then we could sniff as well.
Another question?
Mm-hmm. Oh, right there.
Just, I mean, it kind of goes in a line with usability and safety anyways, where we assume devices do what we ask them to do, even without a malicious user. You know, it just goes towards UIs where this is what was last programmed. This is what the delta is between you know, what was last programmed, what you're changing. You know, that's kind of useful from a doctor's perspective and also tells you, you know, gives you that visibility.
So if you had this sort of a feedback mechanism that you're talking about, it's very tricky to evade the attack because if you present some sort of a pop-up window saying this is the delta that you changed, right? As long as the user can shut the window down or close it in a very fast way, so the malware can do it as well. So even if you show me this pop-up saying, oh, hey, you changed my heart rate to 100, I could just instruct the device, you know, go and click OK in a very fast way, and then you don't see anything.
The slider would have the new setting, what was last programmed. It would tell you
so in a visual manner. Yes. But I could tell you already that that wouldn't work for the majority of users because users, when they programmed the pacemaker, they received a visual feedback that says, they saw pacemaker successfully programmed. And then they absolutely forget everything they saw, and they are like, oh, hey, so this app tells me I did a good job, yay, I get a cookie. And then that's exactly how it works. So it's tricky to sort it out.
Okay, thank you. Let's thank Luka again. Though the last talk of the session is entitled On the Security of Carrier Phase-Based Ranging. The talk is given by Aanjhan Ranganathan. I hope it was almost close. In his talk, he will show that some techniques which should prevent relay attacks are not so perfect as they originally were designed. So he will talk about different methods to overcome distance and to shorten, to extend actually the communication between approver and verifier. Yeah.
It's better?
Yeah.
It's a pleasure to be presenting our work on the security of carrier phase-based ranging at CHES 2017. This is a joint work with my colleague Hildur Olafsdottir and my supervisor Srdjan Capkun from ETH Zurich in Switzerland. So today we live in a physical world where location and proximity are ubiquitously used in a wide variety of systems. For example, contactless access tokens that use proximity information are prevalent today in a number of applications ranging from payment systems, hotel key cards, transportation ticketing, just to name a few. Even modern automobiles use proximity-based entry systems So what happens here is that the car automatically detects whether the key fob is in close proximity to the car and unlocks the car without the need for the user to remove the key from his pocket. Establishing proximity requires estimating the physical distance between two entities. And typically it is determined in a wide variety of ways. For example, radio signals, as we all know, as they propagate through space, they undergo signal loss. So basically, one could estimate based on the signal strength at the receiver, you could estimate the distance the signal traveled. An alternate method is to use the time taken for the pulse to the time of flight taken for the pulse. For example, in our case of the car and the key, one could assume that, let's say, the car transmits a pulse, it travels to the key receives it, processes it, sends a response back. The car now precisely estimates the time of flight, and since we know that the radio waves travel with the speed of light, it is now possible to determine the actual distance. However, most of these distance estimation methods have been shown to be insecure if incorrectly implemented. For example, several attacks have already been demonstrated on these systems. For example, our own group from ETH Zurich showed that even though the car entry systems were designed to open only if the owner is 1 or 2 meters away from the car, it was actually possible to unlock and in certain cases even drive away with the car by simply relaying the radio transmissions between the car and the key. This was actually possible even though the owner or the actual key was several tens of meters away from the car. For example, the owner could be in a payment cashier paying for his shopping goods, and the car can be in the parking lot. So that was actually the distance over which we did the attack. Recently, someone actually did this to a New York Times journalist, and more importantly, when this attack was originally published in 2011, we spent over $1,000 to do this attack. 2017, researchers in China did the exact same attacks with $22 of hardware equipment. So that's how quickly the attack became much more easier to do. So what is the key in these kind of attacks is that it's all happening in the physical layer. The attacker doesn't need to know what is the exact data that is being exchanged between the car and the key. So it's basically independent of any cryptographic primitives that is implemented on top. So in this talk, I will focus specifically on a type of ranging system, which is called the multi-carrier phase ranging system, that is fast emerging as a cost-optimized solution for a wide variety of proximity-based applications. It's low cost, low power consumption, and compliance to popular standards such as Wi-Fi, Zigbee is actually making them suitable for the emerging IoT era. More recently, entire localization schemes leveraging the availability of these carrier phase information from popular networks such as 802.11ac, IoT wide area networks such as LoRa, NB-IoT, and the next generation communication systems are actually being built. I listed some of these applications below, but more references are provided in the paper. Which brings me to the motivation of this work. Security of multi-carrier phase ranging systems have not yet been studied yet. Given the implications of distance modification attacks in the scenario that these systems are deployed in a security critical application such as access control to automobiles, critical infrastructure, and even medical devices are significant. It is therefore essential to ensure the resilience of these systems to modern day cyber physical attacks. Therefore, in this work, we make the following contributions. First, we investigate the security of a carrier phase based ranging system and demonstrate the vulnerability to distance modification attacks. We focus on attacks which particularly results in distance reduction, because these have been shown to be most relevant in a wide variety of security applications. Again, I stress that our attacks are purely at the physical layer. That is, they are independent of any higher level cryptographic primitive possibly implemented on the system. In this work, we actually describe 3 different attack realizations with varying degrees of attack complexity, and in the paper we provide a whole bunch of evaluation regarding their effectiveness under various environmental conditions as well. Also, we practically demonstrate the feasibility of distance reduction on a commercial phase ranging system from Atmel, specifically, we were able to reduce the estimated range to less than 3 meters, even though the actual devices were more than 50 meters apart. So let's get started as to how we do, what is phase-based ranging and how we did the attack. So in a typical phase-based ranging system, this is a pretty old technology, but it's now getting prevalent more because of the emerging IoT requirements and emerging number of devices. So two devices can measure the distance based on signal's phase. So in the scenario, let's say, I'm just using this car and the key as a kind of a tie example. This is applicable to a wide variety of applications. So in the scenario of a car trying to estimate the proximity of its key fob, the car transmits a signal, ranging signal, which is basically a continuous wave sinusoid. The key receives the signal, locks onto this face of this transmitted interrogating signal, and transmits it back to the car. The car basically measures the phase difference between its reference signal and the incoming phase locked signal, and the phase difference directly gives you the distance traveled. As you can immediately see that, of course, there is an ambiguity of n, which is basically the number of whole cycles that are elapsed. And this is a very hard thing to keep track of, number of whole signal cycles that are elapsed. So what people have, what has been proposed in the previous works in the past is that you use multiple frequencies. So for example, you can use two frequencies, f1 and f2, and measure the phase difference of each of them. So for example, for the same distance traveled, theta 1 for a certain frequency f1 is much smaller than theta 2, which is the phase difference of when a frequency f2 is transmitted. So based on these two frequencies, you can now, the distance estimation formula reduces to this, which is basically the difference of the phase differences over the frequency hop. And f2 minus f1 is basically how much you hop in frequency. And more the number of frequencies, the more robust the system is going to be to environmental errors. So what are the ways in which you can attack such a system? How secure is this ranging method? So first, some clarifications regarding our system assumptions, our attacker model. So our system consists of two entities. One is the verifier, which in our case can be, in the tie example, it can be the car, and a prover, which can be analogous to the key, and they estimate the distance between them using multi-carrier phase ranging techniques. Now, we also assume that the verifier and the prover implement some form of cryptographic authentication. Otherwise, things get really trivial and obvious. Now, regarding the attacker model itself, we trust the verifier and the prover and assume that they play fully harnessed roles. What we primarily consider in this work is an external attacker, that is a third entity, trying to reduce the estimated distance. And this scenario is very typical or very applicable to the scenario that I just mentioned regarding the passive keyless entry system, where both the key and the car are fully harnessed, and there is a third entity who is trying to relate the communications and trying to steal your car, for example. So now we will move on to the first attack, which is called the phase rollover attack, and it is the simplest of all the three attacks, but yet extremely effective. So for a fixed, consider this same equation that we saw. Now, the frequency hop is typically fixed in a system. So for a fixed frequency hop, the distance d measured purely depends on the measured phase differences, right? And since they are phase differences, typically in a sinusoid, we all know that the phase is changed from 0 to 2 pi. So basically, when you replace theta max to 2 pi, all you get is the maximum distance is purely dependent on the inverse of the frequency hop. So for example, if f1 and f2 are separated by a distance of 2 megahertz, you have a maximum of 75 meters that you can measure, and then the distance starts to roll back. This is typically not a problem for a non-adversarial setting, because it is assumed that at 75 meters, your devices are not going to communicate with each other, so they don't really care about this problem. However, attacker leverages this maximum measurable distance to actually reduce the estimated distance. So what he does is the following. The same scenario, I replace the car and the key with the verifier and the prover. The verifier transmits the frequency f1, phase we just forward it for simplicity. It's not shown. We forward the signal back to the prover. The prover locks onto the face, transmits back its response signal. And what the attacker does now is that he simply delays the signal by a delta t. What happens here is that irrespective of what the frequency is being transmitted, the delay is always going to be constant. So you simply receive the signal, delay it, transmit it back. So what happens here is that, say, I'll explain what happens here with a short tie example again. Say, considering that the prover is at 30 meters away from the verifier. So without any delay, the estimated measured distance is 30 meters. And once we start delaying the signal, you see that it goes up to 75 meters. And after some delay, it rolls back and then again kicks in. And this was the estimate for the frequency up of 2 megahertz. And since it's the 2 megahertz is the frequency difference, you have this rollover every 500 nanoseconds. So depending on where the where you want to put your prover, you can delay it, the attacker can delay it appropriately. All this is fine theoretically, and however, we wanted to practically evaluate the feasibility of this attack. To test this, we used 2 Atmel phase ranging chips to act as a prover and a verifier. And as for the attacker hardware itself, we used a USRPO, Universal Software Radio Peripheral, connected to 2 directional antennas, one pointed at the verifier and one pointed at the prover. The top figure shows the actual setup. Of course, the 2 devices were not so close. They were actually this far in the corridor. And the whole experiment was carried on in our university corridor on a normal working day. And also, these devices operate on 2.4 gigahertz, which means that you will have interference from other Wi-Fi devices as well that are transmitting on this. So all the experiments were run when there were actually interference. So what we observed is the following. When we placed the prover at different distances, 30 meters, 40 meters, 50 meters, and then we actually saw that the prover and the verifier were actually able to communicate without the attacker's presence. So without the relay hardware being switched on, they were actually able to measure the true distance. And then when the attack was triggered at the place shown, slowly the verifier started reducing its distance, because now we are starting to delay the signals. It started reducing the distance, and the slow gradual reduction is because the verifier is averaging over a number of estimates. And at some point, we ended up with less than 3 meters of distance, even though the original prover verifier distance was about 50 meters. So, and again, I note that these experiments were conducted in a in an actual corridor with full interference from other 2.4 gigahertz channels and so on. So this is from a real world experiment. This can be considered as a real world attack scenario. So, one possible countermeasure is that, of course, we have to delay this by more than a few hundred nanoseconds. So one could potentially think that maybe we could implement some form of rough time of flight estimation to just detect these delays. But what one should remember is that radio waves travel close to the speed of light, and therefore even 100 nanoseconds of inconsistence means that there is an attack possibility window of over 30 meters. But also, even if you implement rough time of flight, there are other attacks which we say in the paper that are also possible. For example, this is the RF cycle slip attack, which is much harder to do than simply delay all the signals, however, still possible. So what happens here is that instead of, the original scenario of verifier transmitting the pulse is the same. However, when the attacker receives the prover's response, instead of delaying the signal entirely by the constant amount, based on the frequency of the signal, he chooses a particular delay and affects the phase difference. So now, instead of affecting the entire slope of theta 2 minus theta 1, we individually affect theta 2 and theta 1. And by this, you can actually introduce these delays, and the delays are much smaller. It's of the order of nanoseconds. And of course, there is a flip and the flop side to this. The attacker now requires nanosecond level control. So he basically needs much higher sampling rate, may also implement using analog delay lines and so on and so forth. However, this attack is very hard to detect. Even without a precise time of flight estimation technique. And if you have a precise time of flight estimation technique, phase ranging becomes redundant, you have other problems, so basically you go in a loop, and why do you even use phase ranging? So another type of attack is that is on-the-fly phase manipulation attack, and this is a much easier attack to do than the RF cycle slip attack. But however, and also it's extremely effective. What we do, the key part is that instead of actually delaying the signal, the attacker, what he does is he uses the standard technique of signal mixing. So what he does is the following. He mixes a specially crafted signal, SIF of t, with the incoming SP of t, and generates the SA of t, which is then transmitted to the verifier. So what happens here is that when you mix these two signals, as you know, that there are frequencies and phase differences being generated, and one important fact is that the mixed signal has to be twice the frequency of the incoming signal, because as you mix the signal, you will account for the frequency conversion also that occurs during the mixing. So the signal is then filtered, and then you have this signal generated as SA of t. Now, what is interesting here is that in order to modify the distance, the attacker has to control this value, theta a minus theta ap, which is basically means that he has to configure theta a such that he can force the verifier to estimate the correct distance. And to estimate theta a, all he has to know is theta ap. This can either be estimated on the fly, or you can know the precise distance between the prover and himself and estimate or predict the correct phase of it. And then he can simply generate these signals and mix an appropriate signal and generate SA of t. So the attack is fairly less complex than the RF cycle slip attack, and also very hard to detect, because the only delay that is being generated here are from the mixers and the low pass filters themselves. So there's very little delay involved, so you need again a very precise time of flight estimator to detect this delay. So bad news galore, right? I kept saying attacks. What are the possible countermeasures? Are there any? Is it even possible to secure these phase ranging systems today? One immediate countermeasure comes to mind as the frequency hopping technique, which is basically what if the attacker doesn't even know which frequency to look for to actually switch for the attack. But this is I would say this is a very fairly weak assumption, because all the attacker needs is maybe a hardware that is as capable as the real devices, and especially for the rollover attack, you don't care about the frequency, you just delay it by a constant amount, retransmit. Another countermeasure which we kept discussing on and off is this rough time of flight estimation. First of all, these devices have very limited bandwidth, so the precision of time of flight directly relates to the bandwidth available, which basically means that with the available bandwidth, it would be extremely difficult to detect delays of less than 300 to 400 nanoseconds. And this is already giving you 50 to 60 meters of attack window. Yet, even with these rough time of flight estimation techniques, even if I assume that somehow we implement this, you are not going to prevent on-the-fly phase manipulation or these RF cycle slip, which just involves a few nanoseconds of delays. And this is only going to be possible with precise time of flight estimation techniques. What about introducing random phase differences at the prover? What this actually forces the attacker is that he has to now estimate the phase in real time, because he now has to calculate what is the phase shift that he has to introduce. So estimating phase in real time is very much possible. However, it's going to take some time, but already, since these devices are low-cost devices, they transmit sinusoids for approximately 100 microseconds, so that the phase lock loops can take time to exactly calculate the phase. So with this big distance, it's fairly easy to estimate the phase correctly. So also, these randomized phase shifted response is not going to prevent simple rollover attacks. So in some sense, without increasing the system complexity, it is extremely hard, or making the phase ranging itself redundant, it's extremely hard to secure these systems. So to summarize, In this work, we investigated the carrier phase-based ranging techniques and showed that it is indeed possible to reduce the distance significantly. If there is one message that I would like you to take away from this talk, it should be, don't use phase ranging for estimating location or proximity in security critical applications. As a side note, we collected all our thoughts from our past research and our current works in a IEEE Security and Privacy magazine titled, Are We Really Close? Verifying Proximity in Wireless Systems, which I highly recommend you to read if you're interested in this topic. Thank you for this opportunity. I am now very happy to take questions.
Thank you for the nice talk. What comes to my mind, you said phase ranging systems are not good for a proximity unlocking system. Would you recommend any other techniques?
Ultra-wideband impulse radio.
Pardon?
Ultra-wideband impulse radio. These are very high bandwidth systems, and they can, that's exactly what our conclusions are in that magazine article. We analyze all the different phase ranging systems, including the phase ranging systems that we talked about, and came up to the conclusion that even if you implement time of flight, you have to implement it in a particular way, and this opportunity is provided by ultra-wideband impulse radio systems. And it's extremely hard to reduce distance in an improperly implemented ultra-wideband impulse radio systems to less than a couple of centimeters. Mm-hmm. And this is extremely secure.
Okay, thank you. Okay, then I would like to thank the speaker and all previous speakers again. From the agenda point of view, we now have a break, including the poster session. The poster session will go until 11 o'clock. Thank you.